Okay, what about something with part B? Melting point of NaF is 993 Celsius. CSCl is 645 Celsius. Go through my list of things. So first step, check the elements. Is it all metal, all non-metal, metal, non-metal? What do I have? Na is a non-metal. Sorry, this is a metal. F is a non-metal. Same thing here. CS is a metal. Cl is a non-metal. So we have an ionic substance. And now we have to deal with ionic bonds. So if it's a metal and a non-metal, there's no intermolecular forces. It's all ionic bonding, and everything has to do with the charge of the Coulombic charge and attraction. Okay, so remember, we have two things involved: the charge of the ion and the internuclear distance. So let's take a look at Na and F, and let's look at CS and Cl. Na is in the first column, it's a plus charge. F is in the second to last column, it's a negative charge. CS is in the first column also, and Cl, second to last column, negative charge. So, is the charge going to impact the bond here? And the answer here is no. Remember, the force of attraction, the attraction is proportional to some constant times the charge of the first thing times the charge of the second thing, all over the internuclear distance squared, okay? So the charges, Q, if the charges are the same, it has no impact. So I have to write that down. I say first, the charges don't impact the melting point because they both have plus or minus charges. So the charges do not impact the Coulombic attraction because they all have plus 1 or minus 1 charges. Okay, so you can write them out. So then it has to be something with internuclear distance. And if I look at the periodic table, where's my periodic table? Here's my periodic table. So Na is here, F is here. Okay, so in the first or second column, first and second row. CS is way down here. Cl is down here. So Na and F is going to be like this. If Na and F are like this, well, CS is way down on the periodic table. That's going to be huge. And Cl is also going to be bigger. Okay, so CS is bigger, Cl is bigger. Well, what do I know about the internuclear distance? What's this distance between these two things here? Okay, this one, it's going to be bigger. So then what I'd say, since the sizes or radii, so radii is like how big the radius is. Radii of the ions in CS and Cl are larger than Na and F, comma. The internuclear distance, AP readers love that word, is greater, is larger in CS, Cl. And so what does that do to my attraction strength? that brings my attraction strength down. So the Coulombic attractions are smaller or weaker. And then that in turn makes the melting point lower. And this makes the melting point lower. Okay, because when we're melting it, remember we're breaking apart this bond when you're melting it. And so that is what's going on when you're melting an ionic substance. Okay, last couple questions. If I look at C, it says a shape of ICl4 negative ion is square planar. Shape of BF4 negative ion is tetrahedral. Well, this one gives you the shape. So let's look at the ion, the things involved. I, nonmetal. Cl, nonmetal. B, it's kind of funky. It's a metalloid / nonmetal, but this looks like it's a molecule because we're talking about tetrahedral things. F, nonmetal. Okay, so I have two things here, and it's talking about shape. And so what should we do if we're looking at shape? Well, I know that I have all nonmetal. It's covalent. They're molecules. And the thing that determines shape, I can't really talk about intermolecular forces yet because it's not asking me about physical properties, but we know shape deals with dot structures. So Lewis dot structures. Okay, so if I see something with shape, I have to try to explain the geometry, maybe hybridization if necessary, or how the electrons are set up. And so I'm going to draw the dot structures for these and see how the electrons are set up and figure out how many electron domains we have. Okay, so that one, we need to draw dot structures. The last one here, ammonia, NH3, is very soluble in water, whereas phosphine, pH3, moderately soluble. Well, here we go. NH3, nonmetal, nonmetal. pH3, nonmetal, nonmetal. Okay, well, what does that tell me? All nonmetals. I'm looking at covalent molecules here. Solubility, that deals with an intermolecular force, right? So remember, intermolecular forces, that is how solubility means if I can interact with the water, I can do that. So I set up my table. I go NH3, pH3, my table, my three forces, H bond, dipole, London. Let's go through them. NH3, do I have H bonding? Well, N's connected to an H. And yes, we have H bonding. pH3, there's no, remember you have to have F, O, or N. Okay, so this does not have it. So immediately it tells me, well, I have H bonding. This is probably what I'm looking at. Dipole, if it has H bonding, it definitely has dipole. This one, pH3, yeah. If you look at the shape of it, the shape is, it's going to be a pyramid, triangle pyramid, so it can have some dipole. London forces, everything has London forces. This one might have a little bit more London forces, but as soon as I see H bonding, this is what I'm going to write about. So I would say NH3 and pH3. So NH3 and pH3 both have London and dipole. Okay, so remember that if it's pyramid, it's asymmetric, right? So this is asymmetric, so it gives dipole. But NH3 has hydrogen bonding, which is the strongest of my forces, which is strongest of the forces. Okay. Since water also has H bonding, what can the NH3 do with the water? The NH3 can interact with the water and is soluble, whereas pH3 is not able to. pH3 cannot. Okay, so that's how you want to think about these problems. Make sure you're thinking about what types of elements there are, writing about interactions, either ionic bonds or covalent bonds, figure out if I need to draw a dot structure, and go from there.